On a number line, numbers 1, 2, 3, 4 and so on are called natural numbers. The natural numbers are denoted by the symbol n. If we include the number 0 with the natural number, then the numbers are called whole numbers. The whole numbers are denoted by the symbol w. All these numbers together with these negative numbers are called integers. The integers are denoted by symbol z. Rational numbers. Now if we see between the numbers 0 and 1 or 1 and 2, we will see numbers like 1 by 4, 3 by 4 and so on. The collection of these numbers is called rational numbers. Rational numbers are denoted by the symbol q. Rational numbers are written in the form p by q, where p and q are integers and q is not equal to 0. Is 2 a rational number? Yes, 2 is a rational number because it can be written in a form p by q, and here q is 1, which is not equal to 0. In the same way, 10 minus 25, etc. are also rational numbers. Therefore, we can say that the rational numbers include natural numbers, whole numbers, and integers. Example. Let's now learn how to find rational numbers between the two given numbers. The given numbers here are 1 and 2. Say 1 is r and 2 is s. To find the rational numbers between r and s, we have to add r and s and divide the sum by 2. So we get 1 plus 2 is equal to 3 by 2. Therefore, the rational number between 1 and 2 is 3 by 2. Similarly, the rational number between 1 and 3 by 2 is 5 by 4. Irrational numbers. You must be wondering if there are such numbers which are not in the form of p by q. Yes, there are numbers which cannot be written in the form p by q. Those numbers are called irrational numbers. For example, square root 2, square root 3, square root 7, 0.10, 1110, 1110, 11110, so on, pi and so on. If we collect all the rational numbers and irrational numbers and put them in a bag, then there will be no number left on the number line. And we call this collection as real numbers. Therefore, a real number is either rational or irrational. Irrational numbers on number line 1. Now we will learn to locate irrational number on a number line. Let us see where square root 2 is located on a number line. For this, we will firstly consider a unit square OABC with each side 1 unit in length. Now by using the Pythagoras theorem, OB square is equal to 1 square plus 1 square, or OB is equal to square root of 1 square plus 1 square, which is equal to square root of 2. To represent square root 2 on the number line, we will transfer the square onto the number line, making sure that the vertex O coincides with 0. Now by using the compass with center O and radius OB, we will draw an arc intersecting the number line. Name this point as P. The point P corresponds to square root of 2 on the number line. Decimal expansion of real numbers. We have learnt about the real numbers. Now we will look at the decimal expansion of real numbers. By this expansion, we can distinguish between rationals and irrationals. Let us first take rational numbers. We will find the decimal expansion of these three numbers. Here we can see that on decimal expansion, the 10 by 3. Here we can see that on decimal expansion of 10 by 3, we get remainders 1, 1, 1, 1, 1. Similarly, the decimal expansion of 7 by 8 gives remainders 6, 4, 0. And remainder of 1 by 7 is 3, 2, 6, 4, 5, 1. Example. Let us now have a look at one example. 1 by 3 is a rational number. The decimal expansion of 1 by 3 is 0.3, 3, 3, 3, and so on. And we can see that 3 is repeating here. We write it as 0.3 bar. Let's take another example. Decimal expansion of 1 by 7 is 0.142857. 1, 4, 2, 8, 5, 7, and so on. Here 1, 4, 2, 8, 5, 7 is repeating. So we can write it as 0.142857 bar. Hence, if a number is rational, then its decimal expansion can either be terminating or non-terminating recurring. In other words, if the decimal expansion of any number is terminating or non-terminating recurring, then the number is rational number. And what do we call the numbers whose decimal expansion is non-terminating, non-recurring? Those numbers are irrational numbers. For example, square root of 2, pi, etc. Representation of real number on number line. We now know that every real number has a decimal expansion. That decimal expansion helps us to locate it on a number line. Let us locate 2.665 on a number line. We know that it lies somewhere between 2 and 3. Imagine to divide it into 10 equal parts. For clear view of numbers, now the first part represents 2.1 and the second part is 2.2 and so on. Here 2.66 lies between 2.6 and 2.7. Now focus on the portion between 2.6 and 2.7. Divide this again into 10 equal parts. The first part represents 2.61, the next 2.62 and so on. Again, 2.665 lies between 2.66 and 2.67. Let us focus on this portion of line and imagine dividing the portion into 10 equal parts. The first part represents 2.661. The second part represents 2.662 and so on. 2.665 is the fifth mark in these subdivisions. This process of visualization of representation of numbers on number line is called process of successive magnification. Operations on real numbers. Can you tell what do we get if we add, subtract, multiply, or divide two rational numbers? We will get a rational number. But if we add, subtract, multiply, or divide the irrational numbers, the number we get is not always irrational. Now think, what do we get if we add or multiply a rational number with irrational number? The answer we get is an irrational number. Let us go through some examples now. Examples. Let's add 2 square root 2 plus 5 square root 3 and square root 2 minus 3 square root 3. We can write it in this way also. Hence, the answer we get is 3 square root 2 plus 2 square root 3. Let's now divide 8 square root 15 by 2 square root 3. We will write it in this way. We can write 8 square root of 15 as the product of 8 square root of the 3 and the square root of 5. Hence, the answer we get is 4 square root of 5. So from these examples, we can conclude that the sum or differences of a rational number with an irrational number is irrational, and the product or quotient of a non-zero rational number with an irrational number is irrational.